This is a summary of what we did in the April 21st class meeting in the morning, transitioning from what I normally call physical heat concepts into chemical heat concepts. So far we've looked at heat change as is associated with phase changes of water. We had three basic equations. Q is equal to mCp delta T. Q is equal to mHV, and Q, the quantity of heat, is equal to mHF. So the heat of fusion equation is relevant down here where you're melting, the heat of vaporization up here where you're boiling something. This equation is used anytime there is a temperature change. So we also use that equation to calculate heat changes during chemical reactions, but this equation doesn't have a chemical equation in it. So here's how they tie together. We spent some time yesterday talking about calorimeters. And calorimeters are devices used to measure heat changes. We talked about it in a previous video in the context of food. If I put a potato chip in the calorimeter, the water would flow out into the water, or the heat would flow out into the water or flow from the water in. We'd measure the temperature change, and then you could use the Q equals mCp delta T equation for the water. We would assume that any heat change that occurred during the chemical reaction would be detected in the water if it was well insulated. So suppose we have a potato chip burning in here. Here's a Ruffles potato chip, and it burns. The energy from the burning potato chip would flow into the water, and we would be able to measure the mass, the heat capacity, the change in temperature of the water, or multiply them together, and we could calculate the actual amount of calories that came from the potato chip. So today we're going to look at the development of a mathematical equation that allows us to calculate energy changes in chemical reactions. And what I'm really working toward is trying to help you understand this chart that I have pulled up over here. These are called heats or free energies, enthalpies of formation. So enthalpy means heat content, and these are chemical compounds or free elements. These numbers over here are the energy changes that are associated with the formation of these compounds from free elements. So let me show you what we mean. So suppose we have some aluminum and some oxygen in the container. If they react and make aluminum oxide, all of the energy change from the reaction here would be given to the aluminum oxide. That's not to say that the aluminum and the oxygen themselves don't have a heat content. They have some potential energy stored in them, but we need to have something to define as zero. Having zero heat content. So it's kind of an arbitrary definition, sort of like if I did over here, if I look up Pikes Peak, it's in Colorado, looks like this. So there's Pikes Peak. It's got an elevation of something around 14,000 feet. But that doesn't mean that it's 14,000 feet from here to the bottom of the hill. It means it's 14,000 feet above sea level. So we arbitrarily said that sea level is going to be defined as zero. As a matter of fact, Denver is called the Mile High City. And if you look at Denver, it doesn't look very high. It basically looks flat right here, doesn't it? So it's a mile because this is a mile above sea level. So sea level is an arbitrary standard of zero. Just like in chemistry, we say that free elements are arbitrarily defined as having a heat content of zero. And free means that the element is uncombined or in a natural state. A natural state meaning that it is in its normal, everyday state. So if I took a sample of aluminum and combined it with oxygen, I'd make aluminum oxide. All of the energy change, by definition, would be associated with the aluminum oxide, not the aluminum and the oxygen, because they're defined as having zero heat content. So if you look over here, aluminum is normally a solid. In its standard state, it's 0 heat content. Arsenic is normally a solid too, and in its normal state, it's 0. Barium, normally a solid. See, all these elements in their normal states are defined as 0. Compounds then, heats of formation of compounds are the energy change when a compound forms from the free elements. All right. So technically then, the numbers on this chart are called heats of formation, or standard enthalpies of formation. And the heat of formation is the energy change when a compound is formed from free elements. Now, there's an equation that we use to calculate energy changes using these heats of formation. So for any chemical reaction, we can say that the change in enthalpy, I'm going to call that change in enthalpy. Okay, so the change in enthalpy is equal to the heat of formation of the products minus the heat of formation of the reactants for any chemical equation. So let's look at an example. So if I have, this is a famous example, aluminum oxide or aluminum metal plus iron oxide, and it'll create aluminum oxide and iron. This is a famous reaction in chemistry. It's called the thermite reaction. Thought I'd just show you really quickly what it looks like. So here it is. We have here the iron oxide and aluminum is in the flower pots.
Once I do, I'm going to drop it in. We're going to step aside.
Sure.
All right.
So the camera will be on this. We'll be just off camera watching with you, but
Here we go.
safety comes first.
All right.
Okay.
I'm going to drop that in and
All right.
go ahead and step this.
All right.
Notice it melted right through the flower pot.
Because what you see dripping out of that is molten iron, over 4,000 degrees Fahrenheit. And down in
So that particular reaction is what we would say is very, very exothermic. Energy is being released. So if you remember the reaction profiles that we did in the previous video, exothermic means you end with less energy than you started, and that would be what we just saw. Endothermic would mean the environment would get colder, we'd end with more energy than we started. So that was a very exothermic reaction. We're going to actually calculate the energy change now for that reaction. All right, so using the equation, the change in heat, or the change in enthalpy, is equal to the heats of formation of the products. The products will be aluminum oxide and iron, minus the heat of formation of the reactants, and those would be the aluminum and the iron 3 oxide. So products, we have to go over here to our data table. For aluminum oxide, it's 1,669.8, and that's a negative sign, so we'd have negative 1669.8. We also have iron over here, so it'd be 2 times whatever iron is. But if you look for iron, you'll find that iron is actually 0. Why is that? Because iron is a free element. So that'd be 2 times 0. I just put that in to remind you that if there is a coefficient, you multiply the number by the coefficient. So what did I just say? If there's a coefficient, you multiply the heat of formation by the coefficient. That's the products. And these, by the way, these are in kilojoules per mole. And if you multiply by the number of moles in the equation, like in this case it was 1 mole, then moles cancel, so you end up with just kilojoules. All right, so products minus the reactants. Now reactants, we've got aluminum, we got iron 3 oxide. So we have 2 times the heat of formation of aluminum, which you should already know. What is that? Okay, plus the heat of formation of the iron 3 oxide, which is right here, Fe2O3, negative 822.1. All right, so what we really end up with then is 1 times negative 1699 is negative 1669.8 plus 0 is just 0, minus a minus 822.1, because 2 times 0 is just 0. you need to know your mathematical operations. Minus a minus is a plus. Okay, so then you pull out your calculator, and we have a 1669.8, that's a negative number, plus 822.1 equals negative 847.7. And that's kilojoules of energy. And once again, it's kilojoules because up here, these are 2 moles, kilojoules per mole, moles cancel, 2 moles, moles cancel, 1 mole, kilojoules per mole, moles cancel, so you end up with kilojoules. So that's an exothermic reaction. So that amount of energy you saw, if they used 2 moles of aluminum and 1 mole of iron 3 oxide, that's that movie we just saw, this, right there, not there, there, and right there. That is the big fire. Okay, so that is probably, I'm guessing they did not use a complete mole of iron 3 oxide, because that would be 160 grams. And I suspect they didn't use more than 80 grams. So the amount of energy that we saw would only be about half this much. So that big ball of fire there is probably, I'm just guessing here, that's about 425 kilojoules. If you change that to kilocalories, a kilocalorie is 4.18 kilojoules. So probably divide that by 4, approximately 100 big calories. And so that amount of energy would be not more than the amount of energy in about a half of a Milky Way bar. So if you look at this ball of fire and think about dividing a Milky Way bar, it's about half that, about half a Milky Way bar, maybe not quite half. That's a lot of energy. And it takes about 2,000 calories to keep you going every day. So if you multiply this by 20, this ball of fire by 20, that's how much energy you use every day just to maintain, to stay alive. Kind of interesting concept, I think. All right, so this is how you calculate the heat of formation, the heat change for a chemical reaction by using heats of formation. It's very simple. It's just products minus reactants. You add up all the heats of formation of the products and subtract the heats of formation of the reactants. That gives you the answer. So I have another quiz that I posted on the website that I want you to do for practice before I make up one is for a grade. And that's already posted as I make this movie, and I'll post this movie in a few minutes.